The central principle of superconductivity is that electrons form pairs. But can they also condense into foursomes? Recent findings have suggested they can. And a physicist at KTH Royal Institute of Technology, Sweden, published the first experimental evidence of this quadrupling effect and the mechanism by which this state of matter occurs. Reporting in the journal Nature Physics, Professor Igor Babiu and collaborators presented evidence of fermion quadrupling in a series of experimental measurements on the iron-based material Ba1-X Kx Fe2As2. The results follow nearly 20 years after Babiu first predicted this kind of phenomenon and 8 years after he published a paper predicting that it could occur in the material. The pairing of electrons enables the quantum state of superconductivity, a zero-resistance state of conductivity which is used in MRI scanners and quantum computing. It occurs within a material as a result of two electrons bonding rather than repelling each other as they would in a vacuum. The phenomenon was first described in a theory by Leon Cooper, John Vadim, and John Schrieffer, whose work was awarded the Nobel Prize in 1972. So-called Cooper pairs are basically opposites that attract. Normally, two electrons, which are negatively charged subatomic particles, would strongly repel each other. But at low temperatures in a crystal, they become loosely bound in pairs, giving rise to a robust long-range order. Currents of electron pairs no longer scatter from defects and obstacles, and a conductor can lose all electrical resistance, becoming a new state of matter, a superconductor. Only in recent years has the theoretical idea of four-fermion condensates become broadly accepted. For a fermion quadrupling state to occur, there has to be something that prevents condensation of pairs and prevents their flow without resistance, while allowing condensation of four electron composites. The Vadim-Cooper-Schrieffer theory didn't allow for such behavior. So when Babiu's experimental collaborator found in 2018 the first signs of a fermion quadrupling condensate, it challenged years of prevalent scientific agreement. What followed was 3 years of experimentation and investigation at labs at multiple institutions in order to validate the finding. Babiu says that key among the observations made is that fermionic quadruple condensates spontaneously break time reversal symmetry. In physics, time reversal symmetry is a mathematical operation of replacing the expression for time with its negative in formulas or equations so that they describe an event in which time runs backward or all the motions are reversed. If one inverts time direction, the fundamental laws of physics still hold. That also holds for typical superconductors. If the arrow of time is reversed, a typical superconductor would still be the same superconducting state. However, in the case of a four-fermion condensate that Babiu report, the time reversal puts it in a different state. The experiments open up a number of new questions, revealing a number of other unusual properties associated with its reaction to the thermal gradients, magnetic fields, and ultrasound that still have to be better understood.